Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 10.4 from your textbook, which was our discussion of the calculus of polar curves. In this video, we're going to work through several more examples of looking at areas and arc lengths of polar curves. We're also going to spend a little bit of time to learn how to determine the area inside of one curve and outside of another, so the area between two polar curves, as well as the sort of area of an intersection between two polar curves. One quick note on this, though, we're not going to learn any sort of new formulas or anything. Everything that we sort of needed to know to do this was covered in that 10.4 part 1, so we're going to continue to use the same area formula, the same arc length formula. So there won't be any new derivations of formulas. And the other sort of second thing to note in this video is that we're going to have a lot of sort of polar curves where the graphs have already been given to us. So some of these might not be of the standard families like the limaçons or the petal graphs or things like that. There'll be some more interesting sort of curves or some mixtures of those so that you guys can see some additional polar curves. You're not expected to graph these yourself. Any sort of polar curve that you're asked to graph is going to be something in one of those three families, either the sort of circle family, that limaçon cardioid family, or that petal graph family. But of course, if we're given the graph, we should be able to sort of work with that. So we'll also just spend a little bit of time trying to identify, if somebody gives us sort of a picture of polar curves, how to get all the sort of most relevant information, even if we're not constructing the graph ourselves. So we're going to start off with a sort of non-standard curve. This is actually what you get when you sort of combine the limaçon idea with the petal graph idea. This is a polar curve here, r equals 2 plus 4 cosine 2 theta. You'll notice that it has that setup of the a plus b, just like we would have if we were studying a limaçon, but we have that 2 theta inside of it, which makes it more like a petal graph. As you can see from the graph of it, what ends up happening is that you once again have 4 petals, but because of the fact that it has that limaçon behavior, this 2 plus 4 cosine 2 theta, the petals are not actually all symmetric. These 2 petals here are different than these 2 petals here. So you can see how the sort of 2 ideas of the limaçon and the petal graph have been combined to make this sort of polar curve here. So we've got 2 things that we're going to do here, and another sort of note, all the examples in this video we're going to just be interested in writing down but not evaluating integrals, because again, mostly interested in this class for the setup of these things. So we're going to write down but do not evaluate an integral for the area inside both of the smaller inner loops. So in other words, in our picture here, we're going to try to determine the area in here and the area in here, so the area of the 2 smaller inner loops. And we're going to try to write down but do not evaluate an integral for the arc length around both of the smaller inner loops. So in other words, the arc length as we do that, and the arc length as we do that. So how are we going to sort of approach this? Well, as you can imagine, we already have the expression here. So probably the things that we really need to think about is, once again, sort of where do these inner loops stop and start? We might also want to think a little bit about how this thing is traced out. So let's first just think a little bit, since we have the picture in front of us, it's tempting to just move straight into computing everything. But do keep in mind, we should think a little bit about where this graph came from. If you think about theta equals 0, you're going to get 2 plus 4 cosine of 0, which gives us 6, which tells us that at angle 0, we're sort of starting here. So it's reasonable, just from sort of smoothness, to believe that we're probably tracing this graph out sort of swinging through here, down into here, through here, out through there, back around, through there, and then back to there. Why is that reasonable? Well, if you sort of try to do other things, notice that you have like sharp corners. That doesn't quite make sense. If this sort of goes in here, again, a sharp corner doesn't really, usually polar curves don't have those. So you can sort of reason out, and you can check by plugging in values, that it probably comes through here, does the bottom small loop first, then up through here, then through here. I also just realized that inner is sort of a bad word to use here, so we should just say the smaller loops here. So let's just cross that out. They're not really inner loops. They're not inside of anything. Let's just call them smaller loops here. Okay, so what that tells us, though, is if you're trying to figure out where they start, where those smaller loops stop and start, you want to make sure that you realize that the first one you're going to run into is actually this one here, and then you actually go through this second one later on. All right, so how do we actually find that? Well, let's go ahead and do that. So to find the start slash end of the smaller loops. Well, we know that these smaller loops have to happen once we get back to the origin. So we can go ahead set r equal to 0. So let's go ahead and try to solve that. 0 equals 2 plus 4 cosine 2 theta. Then you should get negative 2 equals 4 cosine 2 theta. Looks like you should get negative 1/2 is cosine 2 theta. Now you should always be careful when solving trigonometric expressions when the argument has been changed. If you think about what this is really saying, when is cosine negative 1/2? Well, we know that that means cosine achieves negative 1/2 at like 2 pi over 3, and of course plus 2 pi k. And we also get 2 theta equals 4 pi over 3 plus 2 pi k. Now the reason I'm writing out that plus 2 pi k is because when we divide by 2, this period is going to shift to pi. So you always want to make sure that when you have a modified sort of period in here, modified argument, you actually go ahead and solve writing out like this. Now, of course, we could try to make an argument that we only need to figure out the first start. We could say, since we're sort of reasonably sure that it goes like this and comes around to here, we could say, let's just find where you start and go to here, which we can probably assume is like 3 pi over 2 or pi over 2. Most likely pi over 2, because if we're sweeping the angle from 0 and then down to here, this is probably achieved at like theta equals pi over 2 with a negative radius. But again, if you want to find the actual stop and start of each smaller loop, you got to go through and solve it completely like this. If we go ahead and get this, then we can get that theta looks like it should be pi over 3 plus pi k, and theta should be 2 pi over 3 plus pi k. So that gives us solutions like pi over 3 and 4 pi over 3. And this guy gives us solutions like 2 pi over 3 and 5 pi over 3. So it's reasonable to think that this first smaller loop probably starts at pi over 3. Notice that that seems to make sense because as this comes in, notice it makes it in before that pi over 3 that's listed there. And then we come around here and it looks like it makes it back before that 2 pi over 3, which of course is the same as that 5 pi over 3 there. So it seems to make sense that that first one here goes from pi over 3 to 2 pi over 3. So we'll actually get these two there. It also would make sense that we probably swing in here for 4 pi over 3 and exit the second one at 5 pi over 3. Okay, so let's go ahead and make use of this. So we'll say that the first smaller loop goes from pi over 3 to 2 pi over 3. So if we then want to get the area inside both of the smaller loops, what we can do is we can say that for A here, the area is going to be 2 times the integral pi over 3 to 2 pi over 3. I'm doubling it because my pi over 3 to 2 pi over 3 is just going to calculate the area of this one here. So doubling it will give me what's up there. Then we'll have 1/2 and then r squared, which is at 2 plus 4 cosine 2 theta squared d theta. And there we go. There's an expression for the area of both of the smaller loops. Could we do this using symmetry? Well, we could. We could do something like 4 times the integral from pi over 3 to pi over 2. You might say, how do we know that this is pi over 2 down here and not 3 pi over 2? I mean, it looks like 3 pi over 2, but keep in mind if you plug pi over 2 into this, you're going to get 2 plus 4 cosine of pi, which is going to give you a negative 2 radius. So you're facing this way, but you back up to here. Also notice in terms of the angles, it doesn't make any sense to say go from pi over 3 to 3 pi over 2. That's like sweeping out from here all the way to there. That's way too much of an angle there. So we could do 4 times the integral pi over 3 to pi over 2 if you wanted to use even more symmetry, but this should be safe enough because we're just taking the area of one smaller inner loop, doubling it, and getting both of them. Still said inner loop there, just means smaller loop there. Sorry about that. I don't know why I keep saying inner loop. All right, so there we go. There's our area. Can we use this to get the arc length around both of the smaller loops? For sure, same idea. You can get away with the same sort of bounds, 2 times the integral pi over 3 to 2 pi over 3, square root. We need to get our r squared, so we'll have the 2 plus 4 cosine 2 theta, and then squared, plus then if we go back up here, we can just make a quick note, dr d theta. If we differentiate this thing, looks like we should get negative 8 sine 2 theta, because you do need to use chain rule to differentiate that. So negative 8 sine 2 theta, throw that in there. Negative 8 sine 2 theta, square that, and then integrate that whole thing, d theta. So there's the area and the arc length inside both of the smaller loops, or around both of the smaller loops there. Alrighty, so the idea here is to make sure that even when you're presented with the graph of a polar function, even if it's a sort of more complicated polar curve, you want to be able to identify those key features. And notice we sort of did that by first thinking just about how this guy was traced out, starting with angle 0 and letting the angle increase. Meant that we came through here, back through here, then around. That was the smooth way to do that. Then we realized that that meant we had to go through the origin to start that smaller loop. We figured out where that happened, had to be a little bit careful because of the modified argument. So we actually found one solution from here, one solution from here. Notice it made sense to say pi over 3 to 2 pi over 3 because we're thinking about that theta as sort of like a parameter. So we're sort of going as theta increases. So you go from pi over 3 then to 2 pi over 3. That 4 pi over 3 and 5 pi over 3 define the start and end of the other one. So we could have used those as well, as long as we did 4 pi over 3 to 5 pi over 3. And then we just use our standard area and arc length formulas there. All right, let's go ahead and take a look at another one, getting into sort of the last conceptual idea that we want to talk about, which is trying to determine the area between several polar curves. So we're going to actually now see some graphs that have multiple polar curves on them. So we're going to consider the two polar curves depicted below, r equals 4 sine 5 theta and r equals 2 root 2. Now from our knowledge, we know that this guy here has to be a petal graph. So this guy here must be the one in red that has 1, 2, 3, 4, 5 petals because it has 5 theta. And then r equals 2 root 2. You could actually think about what this really means. If you just set r equal to a constant value, that means your radius is always constant. What shape are you drawing when the radius is always the same thing? Well, you're drawing a circle. It's that blue circle there. So just to make a note, this one here is in red in my graph below, and this one here is in blue. And of course, we know that that has to be the case. So we're going to try to do, again, some write down but do not evaluates. For A, we're going to try to do write down but not evaluate an integral for the area inside the first curve. So inside this red one, but outside the second curve. So what does that mean? We want the area inside the petal graph, but outside the circle. So we're talking about this stuff, this stuff, this stuff, this stuff, and this stuff. So the stuff inside the red, but outside those circles. So if we sort of zoom in a little bit, let's just focus on this first one. Always easiest to work in quadrant 1. So let's think about this first one here. If we think about trying to get this, we could, of course, figure out this area and then multiply by 5. Because we've got 5 pieces there. Well, if we want to do that, we probably want to know when they intersect and when they intersect again. In other words, the start and end of this little section here. Once we know the start and end, how are we actually going to get this area here? Well, what we can do is we can measure the area out to our red curve, and that'll measure too much, and then we can simply remove the area to the blue curve. So we can just take the difference between the area inside the red and the area inside the blue, and that'll give us the stuff inside of one and outside of the other. So let's see how to do that. The first thing we're going to need to do is figure out these points of intersection here. So let's go ahead and try to do that. So let's go over here. Points of intersection. Now, points of intersection can be very complicated sometimes when you're doing polar curves because, again, you have non-uniqueness of representations. So when you do this, you always want to make sure that once you solve it algebraically, you go back and you take the time to actually look at the graph and make sure that the solutions you found really do make sense. So in terms of finding the points of intersection, we set them equal to each other, just like we normally would. So we get 4 sine 5 theta equals 2 root 2. We get sine 5 theta, it looks like it should be root 2 over 2. And then, of course, that tells us that 5 theta should be pi over 4 plus 2 pi k. And 5 theta, when else is sine equals to root 2 over 2? That would be at 3 pi over 4 plus 2 pi k. If we divide by 5, looks like we should get pi over 20 plus 2 pi over 5k. And theta equals, what is that? 3 pi over 20 plus 2 pi over 5k. So, since I'm just looking for those first couple points of intersection, we can probably use pi over 20. So that should be from here. Then if I add 2 pi over 5, that's really like adding 8 pi over 20, I suppose. That would be 9 pi over 20. But if I just use the first one here, that would be 3 pi over 20. So if we look at those first two solutions, do those bear out on our graph? Well, visually pi over 20, yeah, that seems reasonable. I mean, there's pi over 6, there's pi over 4. That makes this guy pi over 8. Pi over 20 should be even less than that, and there we go. Seems reasonable. Now, what about the 3 pi over 20? Well, 3 pi over 20, if you think about 3 pi over 20, 3 over 20, that's like 0.15. That's a little less than like 0.16. And notice that that intersection does happen right before pi over 6. So it makes sense that those are our 2 points of intersection, there and there. So you can see again why checking it sort of visually is a good idea here to make sure you're really picking out the right intersections there. Okay, so we're now reasonable in saying that this starts at pi over 20 and ends at 3 pi over 20. So for A here, what we can go ahead and do is we can say that that area, and again, I'm going to go ahead and just shade it in to make sure we're clear on what area we're talking about. Now, let's do it in purple. Why not? We're talking about this area here, these 5 sections. Okay. So that purple area should be 5 times the integral. We got pi over 20 to 3 pi over 20. So pi over 20 to 3 pi over 20. Which function is furthest out? Again, sort of think about it as going out from the radius. It's certainly the red one, which of course is this guy here. So we would take 1/2 times 4 sine 5 theta squared minus the area inside the blue one, right? So if we take that difference, we'll get the stuff in between. And the blue one, of course, is 2 root 2. So we can do minus 1/2 2 root 2 squared d theta. And this should feel a lot like when you did the area between two curves in just back all the way back in chapter 6, right? Area between two curves, we said you just take the integral of their difference. Same thing here. We're just taking the area outside. That's giving us all the stuff from here to here inside the red one. So all of that stuff there. And then we're removing the stuff inside the blue. So again, inside of here, we're taking out all this stuff. What's going to remain is that purple stuff in between. Of course, we can multiply it by 5 and get that. Now, you might say, this was sort of messy with the points of intersection. Could we just use the first point of intersection and even more symmetry? Well, if you think about it, we could actually cut this thing a bit further. If we wanted to, we could cut this in half and just get this here. Then we would only need to know the first point of intersection and whatever angle gives us the very tip there. Now, how would we figure out where that very tip is? Well, if you think about it, that's where that sine function has to be maximized. Now, sine hits its maximum at things like pi over 2 or 3 pi over 2, etc. So the first time it would hit that is at pi over 2. Well, if 5 theta equals pi over 2, then that must be theta equals pi over 10. In other words, that moment where we actually hit the largest radius there is at theta equals pi over 10. So an alternate one is we could say, or we could take the area to be 10 times the integral from pi over 20, that first point of intersection, to that midway point, pi over 10, and then, of course, the same functions in there. 1/2 4 sine 5 theta squared minus 1/2 2 root 2 squared d theta. So either of these are good. The advantage of this one is that you don't have to find both points of intersection, which can get a bit messy. The downside of this one, though, is that you do have to sort of reason out what moment is going to be that largest radius. We know that that happens for sine when the argument is pi over 2. Since we have 5 theta, that means the actual angle should be pi over 10. So either of these would give you the area inside of all those purple sections, everything outside the circle, but inside the petal graph. All right, let's go ahead and give ourselves the same sort of page back and now try to do a different area. Now we're going to write down, but do not evaluate, an integral for the area inside of both curves. And when we say the area inside of both curves, we mean the area of intersection. So what we're going to try to do, if we zoom in here, is we want to sort of determine this stuff, the stuff that is inside both of the curves. Okay. So we want to try to figure out that green area inside of both of the curves. So this is sometimes referenced as the area of intersection, because if you sort of imagine both of these being sort of filled in, this would be the stuff where they would sort of overlap, right? This stuff is not inside the petal. This stuff is not inside the circle. This is the only stuff that is inside both of the graphs. Okay, now this is not the area between two curves, so we have to sort of approach this a little bit differently. Whenever you want to do the area of intersection, the sort of idea is to figure out how you're tracing this out. So what I'm going to do is I'm going to focus on this piece right here. To make this a little bit easier, I'm going to sort of erase this just for a moment so that we can see it a little bit more clearly. Since we took the time on the previous one to go ahead and sort of get that mid value, let's imagine splitting this just for a moment in half. Okay. And of course, we know that that happens at pi over 10. And of course, we also know from our work on the previous one that that intersection, that first one, happens at pi over 20. So what I'm going to try to do is I'm going to try to get this sort of area in here. And the way I'm going to do that is, and let's zoom very far in here, is I'm going to start from theta equals 0, which is where this curve begins. And then I'm going to use the red curve. So I'm going to go out to the red curve to here, to here, to here, to here, until that pi over 20. And then at pi over 20, instead of continuing out to the red curve out here, I'm going to now use the blue curve until I hit pi over 10. So in other words, the way I'm going to build this area is initially I'm going to radiate out to the red curve until I hit pi over 20. And then I'm going to begin using the blue curve the rest of the way. And if I do that, that'll fill in this entire area. So what that tells you is that when you're doing area of intersection, you're going to need two separate integrals. So let's go ahead and do that then. So we would say that this green area here, because we split it in half, there's going to be a multiple of 10. And we're going to put bracket here. So initially, I'm going out to my red curve. And that is going to be the integral from 0 to pi over 20. And I'm using the red curve, so 1/2 4 sine 5 theta squared d theta. And then I'm going to add to that as I go from here to here, but following not along the red curve anymore, but following along that blue curve. So that's going to be the integral from pi over 20 to pi over 10, 1/2, and then we'd have the formula for the radius of the blue, which was 2√2 squared d theta. And there we go. If we do 10 times the sum of those integrals, that'll give us the area of the intersection, or the area inside both curves. Now, what if you didn't want to use that midpoint? Well, it turns out that you would have to then use 3 integrals. What you would need to do is you would need to first have an integral using the red curve up until pi over 20. So from 0 to pi over 20 with the red curve. Then you could go from pi over 20 to 3 pi over 20. Remember, we found that this guy was at 3 pi over 20 in the previous part. And you would do that following the blue curve. But then you would need to follow the red curve back to the origin. How would you figure out the angle where it gets back to the origin? Well, you'd have to set 0 equal to 4 sine 5 theta. Then that would tell you that that happens when 0 equals sine 5 theta, which tells you that 5 theta needs to be some multiple of pi, which tells you that it happens at like pi over 5k. So the first time that would happen would be at pi over 5. So you'd have to have something from 3 pi over 20 to when you get back, which would be at pi over 5. Now, is that harder, easier? No, it's about the same, but this middle is so nice sort of visually, and it's easy to think about exactly when sine achieves its largest value at that pi over 2 for its argument, that I prefer using just 2 integrals there. One to get us up to here, and then another one to follow that there, and then that gives us the area of that in there. Multiply by 10, you're good to go. All right, now this is usually one of the more complicated things to just sort of imagine visually, because we're so used to areas under curves that we just don't have a lot of experience talking about the area swept out as the angle changes. So let's go ahead and immediately jump in to another example of this. So once again, we're going to have another graph that's depicting 2 polar curves. One of them is r plus 2, 3 cosine theta. Notice that this would be a limacon without a inner loop, and it oh, I'm sorry. I think that I miswrote this here. Let's just cross that guy out. This should actually be r equals three plus 2 cosine theta. Yeah, sorry, it should be 3 plus 2 cosine theta. Yeah, because that would not have an inner loop, which is the one that's that's been drawn there. I apologize. I don't know why I mistyped that. So it has r equals 3 plus 2 cosine theta, which is a limacon without an inner loop, and r equals negative 4 cosine theta, which we know is a circle centered on the x-axis. So that tells us that this guy here is that red curve. So this guy is in red, and the other one is in blue there. Now we know a little bit more, like for example, we know that this guy actually has his center at negative 4 over 2, 0. So it's actually centered right there. And you can sort of see that visually. That does look like the sort of center of that graph. All right. So first thing we want to do is we want to write down, but do not evaluate, an integral for the area inside the second curve, so inside the blue circle, but outside the first curve. So we want to try to come up with an integral for this stuff in here. So inside the second one, so inside the blue curve, but outside the red. So once again, we would probably want to think about finding these points of intersection. Now, I would recommend one thing also. As always, just think about briefly how these were traced out. 3 plus 2 cosine theta, when theta equals 0. You start with radius 5, so this guy is sort of sweeping out like this, through here, and then around like that. What about this guy? Well, when theta equals 0, you get negative 4, which means that actually the very first point is over here. And then you get all negative radii, so you actually are tracing this out first. So you got to keep in mind that this guy is going around like that, but this guy is going around like that. So this is going to make finding those points of intersection a little tricky. But let's go ahead and see if we can do it. So, points of intersection. Well, let's try to set these equal to each other. Negative 4 cosine theta equals 3 plus 2 cosine theta. So if we go ahead and do that, it looks like we should get negative 3 equals 6 cosine theta. So it looks like we get negative 1/2 is cosine theta. Where does cosine theta equal negative 1/2? That sounds like it should happen at, what is that, 2 pi over 3 and 4 pi over 3. So if we think about those points of intersection then, that 2 pi over 3 makes sense. That's what we're seeing sort of visually there, and 4 pi over 3 visually there as well, because you can actually see that we got sort of lucky, and they actually landed on things that were on our axes there, right there. Okay, so let's see if we can make use of that then. Well, if we go ahead and try to do this, let's go ahead and sort of cut this graph. So remember, we're trying to figure out this area in here. Okay, so we just figured out that this intersection here starts at 2 pi over 3, and this one here is at 4 pi over 3. Right. At least that's the theta values here. Okay, so let's go ahead and think about how we can measure this. Probably the easiest way is to go from this 2 pi over 3 until we hit this sort of pi component there. All right, so we're thinking about sort of going from pi over 3, so angles like this, until we reach angles like that. All right, so which curve is going to be on the outside? Well, that's going to be clearly the blue curve, and then we'll be subtracting the red curve. So we can get that this purple area here looks like it should be 2 times the integral. We're going to start it from 2 pi over 3, and then we're going to go to pi. So 2 pi over 3 to pi. And our outside one, again, is the blue sort of curve here. So we're measuring from here out to our blue curve each time like that. So that would mean we would have 1/2. Our blue curve is -4 cosine theta, so -4 cosine theta squared minus, and now we want to remove the stuff in here. So we want to remove this stuff in here. So if we do that, that'll be 1/2, and then 3 plus 2 cosine theta squared d theta. So there we go. If we double that, that'll give us all of this area. Could we also just run it from 2 pi over 3 to 4 pi over 3? That does seem safe, because it would just come in through here. We would do these things, then like that. Right, that would give us sort of the area there, like that. And then, of course, we would just remove the stuff in here. Yeah, so we could get away probably without the symmetry here, but again, I like the symmetry approach. So 2 pi over 3 to pi, that's going to give us from here to here, this stuff in there. Double it, you got your overall area. So there we go. That's how to figure out the area outside of one of the curves, but inside the other. Now let's go ahead and see if we can figure out the area of intersection here. So we'll again sort of give ourselves a fresh version of the diagram. Now we want to write down, but do not evaluate, an integral for the area inside of both of these curves. So this time we're going to be trying to get this stuff in here. So as mentioned, we already know that this intersection here happens at 2 pi over 3. And this intersection here happens at 4 pi over 3. So again, the area we're trying to determine is this stuff in here. So we got to be careful, though, because this over here is when theta is 0 on our blue curve. This over here is actually when theta equals pi over 2. How do I know that? Well, that's where this -4 cosine theta would be 0. At theta equals pi over 2, that cosine is going to give us 0 there. So what we want to do is we want to start from that pi over 2. Then we're going to follow out to our blue curve until we reach that 2 pi over 3. That'll give us this stuff. And then we'll start following the red curve until pi. And then we can double that. So if we sort of draw that in, this green area in here, the area inside of both of the curves, well, what we're going to do is we're going to say that that green area is going to be 2 times the integral. Like we said, we're not going to start from theta equals 0 because that's over here. It takes us all the way to pi over 2 to get to here. So we're actually going to run it from pi over 2 to 2 pi over 3. So the first part is going to be the integral from pi over 2 to 2 pi over 3, 1/2. This is where we're using that blue curve, which is -4 cosine theta squared, d theta. And then we're going to add a second portion, which, like we said, is where we're going to start from 2 pi over 3 and then keep hitting out to that red curve, which is going to be from 2 pi over 3 to pi. So 2 pi over 3 to pi, and then we'll be using the red curve, which is 1/2 times 3 plus 2 cosine theta squared, d theta. Close up that bracket, figure out whatever that is, multiply by 2, and you have the area of intersection there. Just to make sure, if we look back at this page, remember this was incorrect. It's r equals 3 plus 2 cosine theta. So, main thing to recognize here is that this curve is not traced out the way you would initially expect. Whenever you're sort of given a graph in polar coordinates, it's always worth taking a little bit of time to think about where this stuff came from. So this blue curve actually started here at theta equals 0, came all the way around to here by theta equals pi over 2, and then it's actually back to here by theta equals pi. That's why we were running it not from 0 to 2 pi over 3. That would be all this stuff, which of course we have no need of this. We wanted to run it from here to here, pi over 2 to 2 pi over 3. Okay, let's try one more example of this. All right, so once again, we have it depicted for us. We have r equals 3 plus 2 sine 2 theta, which once again you can sort of think about as a new type of polar curve. It's another modified limosone and petal graph. This time, though, because that 2 is less than 3 in magnitude, we don't have those extra little pieces, so you almost get like this sort of peanut type shaped here. And r equals 4, of course, is the blue circle there. So this guy is there, and this is right there. All right, so once again, we want to start by trying to get an integral for the area inside the first curve. So inside this stuff, but outside the second curve. So outside the second curve. So we want the stuff inside the red, so in here, but outside the second curve, outside the blue. So we're trying to get this stuff in here and this stuff in here. So how do we want to approach this? Well, once again, we could think about trying to find these two intersections and going from here to here. That would be fine. Or we could think about where this is, go from here to here. Either way. Let's go ahead, though, and first just check to make sure we know how these things are being traced out. When theta equals 0 in here, we get a radius of 3, so we must be here. And then we're swinging around like this, so everything looks pretty normal for that. And for r equals 4, well, it's just always radius 4, so there we go. All right, so let's go ahead and try to find these intersections, and let's also find that value there. So for points of intersection, we can go ahead and set these equal to each other. 3 plus 2 sine 2 theta equals 4. That means we get 2 sine 2 theta equals 1. We get sine 2 theta equals 1/2. That means we should get like 2 theta. When is sine 1/2? Well, it'd be pi over 6 plus 2 pi k, and 2 theta equals 5 pi over 6 plus 2 pi k. Divide through by 2, we get pi over 12 plus pi k, and we get 5 pi over 12 plus pi k. So our guess is that this is probably that pi over 12, and that 5 pi over 12 is less than pi over 2, so that's probably that right there. So if we actually look at this thing, does that make sense? Well, if we look there, seems reasonable to believe that that is indeed pi over 12. It looks like it's halfway between the pi over 6 and 0, so looks like that's pi over 12. And this guy up here looks like that's 5 pi over 12. We should be all good with this. Okay, so we can sort of label that on there if we would like. We're saying that that's pi over 12, and that's 5 pi over 12. Okay, could we also figure out where this happens? Well, that's where this red curve achieves its maximum radius. You can see it's where it's the furthest out. Of course, we can say again, that happens when that 2 theta equals pi over 2. So this must occur right at pi over 4. Okay. So we now know sort of some of the key moments when this stuff happens on this curve. So if we want to come up with an area for the area inside the red but outside the blue, If we shade that in, we're looking for this stuff here and this stuff here. Again, I'll just go ahead and maybe use the maximum sort of symmetry. So we'll go to there and we'll multiply it by 4. So we can say that this area is going to be 4 times the integral from pi over 12, which is where we're going to be starting this, and then we're going to pi over 4. So, and then we're going to be taking the difference, 1/2. The outside curve is that red one, which is the 3 plus 2 sine theta, 2 sine 2 theta squared, minus 1/2 times the inner graph, which is that 4 squared d theta. So this here will measure this area right in here. Multiplying it by 4 gives us our overall area there. All right, very last one. Let's try to find the area of intersection here. So if we want the area of intersection, okay. So for area of intersection, we want the area inside both of these curves. So we want all of this stuff. So once again, let's sort of label our information that we have so far. We have that this is pi over 12. This occurs up here at pi over 4. And this occurs, we found, at 5 pi over 12. So what kind of symmetry could we use here? Well, if we think about it, we want to sort of trace out following to here. But then we have to make sure that whenever we're in that pi over 12 to 5 pi over 12, we follow that sort of blue curve. And then we need to trace back along the red. So the symmetry may be a little bit harder to sort of visualize here. So let's actually sort of draw in a little bit more, just to sort of view this. Okay. So what if we actually follow this blue curve along to here, and then follow this all the way down to here? Then we would need to know that point of intersection, but that's not impossible to do. We could also, follow it from here, and then follow this blue curve to here, so we need to know that point of intersection, and then follow this all the way over to here, and then follow that there. It doesn't look like there's any way to sort of do this without needing at least sort of 3 integral pieces here. So let's go ahead and sort of take the sort of simplest approach we can sort of find here, which is let's go ahead and follow this, like we sort of said, from here to here, and then down through here to here, and then from here to here. So it should be pretty clear that this guy is 5 pi over 4. That's just because it's got to be on the same line as that. As for this over here, well, we can actually use the fact that this has to be on the same sort of line there, add pi to it, and get that this is 13 pi over 12. So what we're going to do to get the area of intersection here is we're going to start from this pi over 4. We're going to follow this curve. Then at 5 pi over 12, we're going to follow the red curve until we get to there. And then we're going to finish back with the blue. And then that will give us all of this area. We can double it, and we'll call it good. So if we actually shade in the area we're trying to get, which is all of this stuff in here, well, we would say that that green area is going to be 2 times the first integral we chose to do was from that pi over 4 until this intersection here, 5 pi over 12. This is where we're going to be following the blue curve. So it would be pi over 4 to 5 pi over 12, 1/2, and it would be 4 squared d theta. Then we're going to be following this 5 pi over 12 all the way to 13 pi over 12 along the red curve. So integral 5 pi over 12, 13 pi over 12. And of course, now we're following the red curve, so 1/2. And the red curve is 3 plus 2 sine 2 theta squared d theta. And then we have one more piece, which is then just going to follow from here to here, again following the blue curve. So we'd have the integral, and that would go from 13 pi over 12 to that 5 pi over 4, 1/2 4 squared d theta. If we calculated all of those, added them up, and then doubled it, we'd have that overall green area. Is that one pretty messy? Absolutely, right? These can get very sort of messy when you have all these different sort of pieces. But the main idea is that when you're trying to get area of intersection, you want to make sure you're following the curve that's on the inside. So notice from here, we're following this to here. That gave us that. Then we're saying from here to here, we're following this. So that gave us all that. And then from here to here, we're following this. So that gave us all that. Double that, and we have all of the green area. Well, that's our last example. This finishes up our section 10.4, finishes up our class overall. So congratulations, and this is us signing off.